All right, so let's begin with this first proposition. We claim that every tree that has at least two vertices has a leaf. Note that that's as strong as possible because a tree with only one vertex has no edges, and hence is degree 0. So let's do a proof by contraposition. Let's suppose G is a graph that has no leaf. So in particular, for every vertex in your graph, the degree of that vertex is not 1. Well, let's consider the cases. Suppose that there's a vertex with degree 0. Then either your graph has only one vertex, or you have an isolated vertex separated from the rest of the graph, so G is not connected. So we see if you don't have a leaf, then you could be a tree with one vertex, or you're disconnected. Okay, let's consider the other case. Suppose that for every vertex, the degree of V is at least 2. So we've ruled out degree 0, and we're forbidding degree 1. Then, as discussed previously in this course, G must contain a cycle. So if for every vertex, the degree of the vertex is not 1, we see that we have something that's not a tree because it's either disconnected or has a cycle, or it has only one vertex. So taking the contrapositive, if you've got a tree with at least two vertices, then it must have a leaf. All right, so now we're going to discuss tree properties. So I'm going to strengthen a claim from the textbook. We're going to claim that every tree with at least two vertices has at least 2 leaves. So the book only points out they have 1, which is generally the version we're going to use. So suppose we have a tree that has at least 2 vertices, and let P be a maximal path of the tree. Let's write P as V0 through Vk. Notice that if k is equal to 0, so the path is length 0, then we run into a problem that there are no paths between distinct vertices. Why is that? Because if you have 2 vertices in your tree, and we know there's at least 2, the fact that they're a tree means they have to be connected by a path, which means you have to have at least an edge, which immediately implies that the maximum length path has length at least once. All right, so one of the things we have studied before is that if P is a maximal path, then any neighbor of the endpoint vertices has to lie on the path. So suppose that the neighborhood of the last vertex consisted of more than just the second to last vertex. Then it has to have a neighbor that's far earlier in the path, and as discussed previously, that means you can form a cycle. So this is the usual drawing where we've got our path, and we found an edge earlier on, so you create a cycle, which contradicts the fact that we're starting with a tree. So this means the only neighbor of the last vertex is the vertex right before it, which means this vertex on the end of our maximal path has to have degree 1, which makes it a leaf. By the same argument, V0 is also a leaf because if it has a neighbor, its neighbor has to be on this maximal path, and if it has at least 2 neighbors on the maximal path, then you can create a cycle. So one of the reasons why we're interested in showing that there are leaves is that we've got this nice feature, which is that if you take a tree T and take a leaf L, then deleting that leaf from the tree gives you a new tree. So this is often used for induction arguments to prove results on trees, because you can do induction on the size of the tree by deleting one leaf at a time. In general, deleting a random vertex from a tree will not give a tree, so this is useful. So let's do this argument. So we want to argue T minus L is a tree. So first, suppose T minus L contains a cycle, and the vertices on that cycle are also in T, and so T has a cycle, which contradicts the fact that T is a tree. So we see that T minus L is acyclic, so that's half the definition of being a tree. So now we need to show that T minus L has a path. So take 2 vertices in T minus L. Since T is connected, there must be a path in the original tree from X to Y. And let's write the path is V0 through Vk, so V0 is X and Vk is Y. So we do have a concern about what would happen if L was on the path. So, we've got this path. We're concerned about what happens if L is in the middle. Well, if L is in the middle of the path, then we see that we've got these two vertices before and after it on the path. And due to the definition of a path, these vertices have to be distinct, which means we have two distinct edges incident to L, which contradicts the fact that L is a leaf, because we now see that the degree is at least 2. So if the path goes through L, then we have a contradiction. Therefore, the path has to avoid L. In particular, that means no vertex on the path was L, which means P is actually a path from X to Y in T minus L. Thus, T minus L is connected, and hence a tree.